Into kind of the next big topic in Unit 1, and that is continuity, okay? And I've thrown that word around a lot. We've talked about things being continuous, things not being continuous, but now what we need to do is nail down what does that actually mean, okay? And so this first part of the lesson is talking about something we've actually already discussed this. You've heard all these words before, but we're just going to kind of nail down and formalize our definition here of the different types of discontinuities. So I'm going to slide this up just a little bit so we can see all three at the same time. We're looking at, again, this is types of discontinuities, and there's three main types. There's the hole, the asymptote, and the jump, okay? And again, we've referred to all three of those before. You've seen them in action. The hole and the asymptote kind of go together. And then the jump is sort of its own thing, and I think you'll see why in just a minute. But I'm going to kind of do this to just kind of separate them. The hole and the asymptote both come from the same place, okay? They both come from the same types of functions. And so really the issue with both of these, the thing that creates this discontinuity, is having a denominator equal to 0. That's what we have to be on the lookout for, is if we have a denominator equal to 0, it's going to cause one of these two things to happen. This is the difference between these two things, whether or not they are removable. But I think I'm actually going to start by writing like an equation for the function type, and so you can see what's going on here. And I'm going to try my best. I didn't create these graphs, but I'm going to try to write equations that will line up with what the graph actually looks like. So if I were to go graph this function, let's see if I had x minus 2 times x minus 5 and x minus 1, and all of that over x minus 2. Okay? That might make a graph that looks something like this. And if you don't know how I came up with it, that's totally okay. Like I said, I'm just trying to write an equation that sort of matches what's going on with the graph here. But you'll see these are called rational functions, where you have like a big ugly numerator, a big ugly denominator, and you have to figure out how to deal with it. This function might be something along the lines of like f of x equals 3x over x minus 3, let's say. And again, I don't know if that's exactly that graph, but it's awfully similar. This is also a rational function, right, where I've got a numerator and a denominator. So what I want you to notice is that in both of these examples, I have stuff on the bottom. I have x's on the bottom of my fraction, and that's where we have to be on the lookout. We have to be worried about what would go in here that would make this x equal to 0. Or, I'm sorry, the denominator equal to 0. What would x be to make the denominator equal to 0? In this case, I couldn't let x be 2. I'm going to have an undefined value at 2. In this case, I have an undefined value at 3 because those will give me zeros. But they show up differently in the graphs. This one would make a hole in the graph, which means the rest of the graph looks totally fine, and then there's this tiny little pinhole that if you were to actually make this graph on your calculator or something, you probably wouldn't be able to see that. This one makes a giant asymptote where the entire graph breaks in half. The difference between those two things is whether or not the discontinuity is removable. So in this case, you'll notice I put an x minus 2 up on the top as well. And so those two things cancel each other. That means this is a removable discontinuity. For the asymptote, there's nothing up top that can cancel with that x minus 3, and that's why this creates an asymptote. This is not a removable discontinuity. So these two things are kind of two sides of the same coin, where one is removable and one is not. And that is the difference between them, is that this one will make a hole in the graph, this one will make an asymptote. Okay? The jump discontinuity, that's this guy down here, these typically only happen when you have those piecewise functions where I have like literally forced this to happen. I've created this like Frankenstein function where I'm putting multiple pieces together that don't really fit. Okay, so just as an example of this one, these ones you're always going to recognize because these are the ones in the big brackets like this. And let's see that this equation would be 1/2 x plus 1, I believe. And this equation here would be something along the lines of, oh, let's see, negative x minus 4 squared plus 5. If you thought about that hard enough, you would understand where I came up with that equation from. That's an algebra 2 thing. That's not something you have to know here. So it's these two functions, but you'll notice that at 3 is where this break is happening, where I have this gap between the two. So I'm going to say this is true when x is less than 3, and this piece is true when x is greater than or equal to 3. And so that forces me to have a discontinuity at 3 because these two graphs don't actually touch. Okay, so now we're going to look at some examples where I give you equations like this, and and I'm sorry, this is not a removable discontinuity. The jump discontinuities, those cannot be removed because they're not even things that could cancel here. Okay, so back to what I was saying. Now we're going to look at some examples that are like these equations, and we're going to try to figure out where the discontinuities are. Okay, so notice the directions say determine the location and the types of the discontinuities. So let's start with just location. We're on the lookout for denominator equaling 0. Okay, so I know for sure here I'm going to have a discontinuity at x equals 5. What I want to ask myself is that removable or not? Well, since there's no x minus 5 on the top, it is not removable, and that means that this thing is going to be an asymptote. By the way, I meant to say this on the front page. If you want to flip back there and write this down, you can. But you will see some textbooks and worksheets and stuff like that that refers to asymptotes as infinite discontinuities. So if you ever see a discontinuity where you're being asked about an infinite discontinuity, it's talking about an asymptote. Okay, in the next one, I know for sure I'm going to have to factor the bottom of this because that's what's going to tell me where my discontinuities are located. So I'm going to start with that. Let's factor down here, and this looks like a plus 5 and a minus 2, I believe. So I know right now that I'm going to have a discontinuity at negative 5, and I'm going to have a discontinuity at positive 2. I know that much. But I can't figure out what type they are until I look at what's happening up here on the top. On the top, I'm going to have to factor this 2. And let's see, I think I'm using 6 and 2, so x minus 6, x minus 2. Because that helps me know whether these discontinuities are removable or not. I see that the x minus 2 cancels, which means this is a removable discontinuity. And so that means the type of discontinuity would be a hole. When it's a removable discontinuity, it forms a hole. But the x plus 5, that is not removable. It doesn't cancel with anything. So that is just going to form an asymptote. Okay, I know the next one, the factoring, is a little bit tricky. So if you want to pause the video and maybe try to factor it on your own, that wouldn't be a terrible idea. On the bottom, I'm going to pull out an x, and so I'm left with x and then x minus 4. And so right away, once I know what my denominator is doing, that's where I know that I have some discontinuities, 2 of them. This one's going to just be at x equals 0. This one would be at x equals 4. Okay, so I know that's where my discontinuities are located. To know if they're removable, I have to look at what's happening up there on the top. And so I'm going to pull out an x squared out of both of them. And then I'm left with an x squared minus 4. Now be careful here. I could factor this further. Okay, if I factored that further, it would be an x plus 2, x minus 2. I don't really need to because all I'm checking for is can anything cancel with the bottom. The 0 is coming from this x right here. And I do want you to notice that this x could cancel with one of these x's here. So my x's do cancel here. That means this thing is going to form a hole. But the x minus 4 does not cancel because this is not the same thing as x minus 4. So if it doesn't cancel, that's going to form an asymptote. Okay, and this last one. This last one is a piecewise function. And so I just want to double check here, but neither one of these has any discontinuities that we need to worry about. And I know that because we know what these graphs look like, right? This is a parabola and this is a straight line. Okay, so no holes, no discontinuities, nothing like that. What I do have to be on the lookout for here is what is happening at 1. Okay, if it's a piecewise function that changes from one graph to the other at 1, it's possible there's a discontinuity there, but not guaranteed. I don't know for sure that there's a discontinuity because I don't know, maybe these graphs touch. Maybe they share that point in common. So what I'm going to do is I'm going to plug the 1 into the top, and that's going to equal 2. And I'm going to plug the 1 into the bottom. That equals -1. Okay, so that's enough to tell me that this is essentially limits that I'm finding, right? This is the limit from the left. This is the limit from the right. There's clearly a break in the graph here. This graph breaks at x equals 1. So I would say that I know I have a discontinuity at x equals 1. And I'm going to refer to that as a jump discontinuity because I am literally jumping from this function to this one. And that's it for that little piece of the lesson. Today's lesson is going to include this and then the next page, which is on the definition of continuity. But for the types of discontinuities, this is all you need to know. All right, have a great day.